Hi everyone, the topic of this masterclass is point cloud-based simple estimation, which aims to estimate the 3D non-rigid motion field of point cloud from dynamic sense. This technique is very important for autonomous systems because it can output a current point-wise motion field from the input point cloud captured from LiDAR or radar. And it can also be used for many downstream tasks for robots and autonomous vehicles. So before we go to the simple estimation, I'd like to give you some background knowledge about how a human visual system infers the motion of the object. As we all know, the retina behind our eyes is the place where the image falls, and some layers of neurons there can retain some motion field signal to our brain. However, our brain cannot directly guide the motion of the object from the motion field, because this motion field is the result of both eye movement and the object movement. So to infer the motion of the object, our brain needs to discount the eye movement. There are two theories about how our brain gets the eye movement signal. Figure B is a flowchart of one of this theory called the outflow theory, which is proposed by Helmholtz, a very famous psychologist in the 19th century. The theory said the eye movement signal can be an inferenced copy of the motor command that controls the movement of the eyes. Another theory is called the inflow theory. Different to the optical theory, it said that the eye movement signal comes from the eye muscle sensors. For this class, we don't have to know which theory is better and correct. But my purpose of showing this slide is to let you know, let you keep this idea in mind that the ego motion and the motion of the objects of the scenes are totally different things, and the motion field output by our retina can be impacted by the relative motion between our eyes and the scenes. Now you know how our human visual system infers the motion of the scene. But for our IS students, what we care more is how our computers could estimate the motion of the objects. Is it in the same way as our human visual system? My answer is yes. Here in this slide, I compare the process of inferring the motion in our visual system and the computer. I can say the camera we use can be seen as a retina, which can capture the images. Well, we use some specific algorithm that can sometimes be embedded in our camera. We could retain the motion field to our computer. The motion field can be seen as a retinal motion signal in the upper figure. And the sensor MU in the down figure can give the ego motion to our computer, is equivalent to the eye muscle sensors in the up figures in our eyes. Given the motion field and the ego motion, the computer can compute the motion predictions of the objects in the sense. So that's how our computer visual system infer the motions of the sense. So let's move to the definition of the optical and the scene flow. Optic flow is a 2D motion field of the pixels in the image plane. For each pixel, the output has two values indicate the motion along the vertical and the horizontal axis, respectively. While scene flow is the 3D motion field of the points in the scenes. For each point, the output has three values indicating the motion along the x, y, and z axis. So scene flow is actually an uplift of optic flow, and its projection to an image plane becomes a 2D optic flow. Also, optic flow and scene flow are low-level understanding of dynamic scenes and can be used in high-level downstream tasks. The optical estimation is a very basic topic in computer vision and has been developed for about half a century. There are many famous classical methods for optical flow estimation, such as the Lucas-Cannon method, which estimates sparse optical flow, and the Hornstrunk method with output more dense flow, and the method's epic flow, which was based on feature matching. But in the past decade, the mainstream optical flow community is deep learning based methods. The FlowNight 2.0, the PWC Night, and the masked flow night are very famous ones among this type of methods. The reason why optical flow attract much research attention is that it has many applications for our real world. For example, it can be used in object tracking and detection. This figure shows how optic flow can be used for visual tracking. And you can see the displacement of the whole object can be easily obtained after we estimate the optic flow within the bounding box. So that's all about optical flow. Let's go back to our focus topic, the thin flow. The thin flow definition was first proposed in 1999, a paper called Three-Dimensional Thin Flow, which combines optic flow and the depth information of the images to estimate the thin flow. Since the similar work, many methods tried to improve the performance by joint estimating the structure and motion from the stereo images, mostly in a variational setting. Some methods use the regularization for smoothness, and some adopt the assumptions of local rigidity. To help you understand this type of method better, I snipped a figure from one of these papers. And you can see using the stereo camera, we get observation of one point from two different views, and then we can jointly optimize the 3D position of the point and its 3D motion using some techniques. With advent of community depth sensors, you can see in the left figure, it's feasible to estimate the thin flow from the monocular RGBD images. In the past decade, many methods are proposed to use RGBD sensors. Some generalize variational 3D flow to 3D flow, and while some methods try to explore it more geometric cues provided by the depth channel. The content in the last two slides is about image-based thin flow estimation. The method worked on the RGB and depth images and can output the dense thin flow for every pixel. Recently, there is another research direction arising. This is point cloud-based thin flow estimation. The method of this type uses the raw point clouds as the input and output the thin flow for its points in the cloud. Here in this slide, we compare the pros and the cons of the point cloud-based thin flow estimation. The first advantage of point cloud-based estimation is that they directly optimize for the 3D thin flow. They don't need to optimize for the immediate stuff, like the optic flow or the disparity map. Also, point cloud-based estimation can utilize other sensors besides RGBD camera, such as LiDAR and millimeter radar. Moreover, unlike classical image-based estimation, the methods based on point cloud would be faster and efficient. Don't need to take several minutes to estimate the thin flow. Last but not least, with LiDAR and radar as the main sensor, the sensor flow can be estimated in a far range, even 100 meters away, and will not suffer from limited baseline distance, and unlike the stereo or the RGBD camera. But for every coin have two sides. Point cloud-based estimation also has some cons. Firstly, its idea is sparse. Unlike the dense image data, it lacks semantic information. Secondly, the data from point cloud is non-structured and harder to handle than the grid image pixels. Another challenge is that they are limited to prior works in this area. Now, this slide, we come to the main topic of this class, the point cloud-based simple estimation. Before 2019, there are only classical methods, mostly based on energy minimization or partial filters, to solve the problem of motion estimation of each point. But starting from 2019, more and more deep learning-based methods come to the fore and have already dominated this area. Here you may want to ask a question, why is deep learning based method better? Why everybody should research them? Here are three main reasons. Deep models can be trained in end-to-end manner. We don't need to work on feature engineering or design in complicated classifiers. Another reason is that deep methods are data-driven, which can utilize large-scale data sets for training and generally perform better using more data for training. The third reason is the deep neural networks can exploit more hidden features from the point data, which is very intractable for classical methods. So this masterclass only introduces works using deep neural networks in later slides. There are two types of learning paradigms in deep learning. One is supervised learning and another is unsupervised learning. For point cloud-based simple estimation using deep neural network, we can also split our methods into these two types. In supervised methods, we can train the network using ground truth labels to update the parameters of our deep model. The top figure shows some ground truths of the scene flow. The arrows in the figure indicate the 3D motion field of these points. But one problem is for simple estimation, annotating scene flow is very expensive on real data. There doesn't exist any large-scale data sets with scene flow annotations. So many works choose to use synthetic large-scale data set, which can be obtained by popping up disparity maps and optical flow ground truth of the stereo images to our 3D point cloud. Therefore, one big problem of supervised method is they have low generalization ability to our real data when trained on synthetic dataset. And for the unsupervised methods, also called self-supervised method, we can train the network without annotated labels because our design framework can exploit supervision signal from the data. For example, we can design specific self-supervised losses. As you can see in the bottom figures, the nearest neighbor loss and the cycle consistent loss can introduce some constraints to the output of the network, and thus they can provide the supervision signal. However, without the hard supervision from ground truth labels, self-supervised method usually have secondary performance. From this slide, I will introduce several methods on supervised and self-supervised simple estimation. The first work I'd like to introduce is a very famous one called FlowNet 3D. It's the first deep learning-based method on point cloud simple estimation. The neural network architecture can be seen in the bottom figure on the right. Its input is two sets of points sampled from two consecutive point cloud, and the output is a simple estimation of the first point cloud. Here, for each input point, the input feature can be its XYZ coordinate and can also include other features, such as color and LiDAR intensity. The main innovation of this framework is that they propose two new learning layers, the flow embedding layer and the setup control layer. Here, the set control layers was borrowed from another famous paper called PointNet++, where the set control layer is a basic point cloud operation model. In this method, they use the set control layers to extract the deep features from its point cloud. And to correlate the features from this two-point cloud, they proposed a flow embedding layer and continue to learn deeper features from the new embedding. Finally, they proposed a novel setup control layer, which can be seen as the inverse operation of the set control layers. With these layers, they can upsample and propagate point features in a learnable way. In the experiments, they not only conduct the experiments on real data and also use synthetic large-scale data for training. Another paper I want to introduce to you is called Weakly Supervised Learning of Rigid 3D Flow. The authors of this work argued that the four supervised methods trained on simulated data suffered from low generalization, and the unsupervised methods suffered from reduced performance. So they tried to seek an optimal balance between the supervision efforts and the performance. The supervision signal used in this method is weaker than the simple ground truth. One supervision they use for network training is the background masks, which indicate if each point is from the background or from the rigid multiple objects. And another supervision signal is from the ego motion. These two supervision signals can be easily obtained from many large-scale real data sets and don't need much human efforts. Another observation of this work is that most dynamics are attributed to rigid object motion. So instead of estimating per point motion, they just need to estimate the background motion, which is induced by the ego motion and object level motion. That's a very sensible idea, especially for vehicles in autonomous driving. As you can see in their framework, the components they estimate are the object masks, object transformation parameters, and ego motion. With the supervision signal from the ego motion and the background mask ground truth, they can compute their designed supervised losses and train the network using the gradient. Now we have seen two supervised methods for point cloud-based simple estimation. However, as I said before, learning-based methods for simple were trained primarily on synthetic data sets, which limited the effectiveness of such methods in real settings. To overcome this problem, some researchers proposed the unsupervised methods for simple estimation. Their framework can train the neural network without any human annotations and can be able to mimic the supervision created by human annotation using their losses. The method introduced by this slide is called Just Go with the Flow. It's utilized two self-supervised losses called the nearest neighbor loss and the cycle consistency loss. The NN loss considers the nearest point to the predicted translated point as the saddle ground truth association. In other words, the NN loss pushes one point to flow toward occupied regions of another point cloud. The cycle consistency loss allows the prediction to be temporarily consistent. To compute this loss, they input the predicted translated point cloud and the original point cloud to the network, and estimate the reverse flow. The loss function computes the distance between the predicted flow and the reverse flow. With these two losses, they could train a thin-flow network over large-scale and annotated dataset. There are many other supervised and unsupervised thin-flow estimation methods in literature, but we have limited time for this class, so I just list 3 papers I would like to recommend to you if you are interested in this topic and want to know more. The first paper is called the Point PwC Night. It's another famous paper in this area, and they proposed to 3 novel losses for self-supervised training. The second method is called a slave. The method didn't need to downsample the point and could input any numbers of points to the network. Last one is called self-point flow. Different from another unsupervised methods, they generated and refined set labels for training instead of using self-supervised losses to provide a supervision signal. As a low-level understanding of the scene, point cloud-based inflow estimation has many downstream applications. For example, it can be used to align two scans because it has naturally existing correspondences. And it can also be used for non-rigid alignment because it can output per point motion field. Simple prediction can also be used for motion segmentation when combined with simple clustering methods. It can also be used for accurate data aggregation across different sweeps. I believe that in the future, simple estimation can be utilized in more applications and can induce more benefits for autonomous systems. Thanks for your listening.